The world of computing in the early 1990s existed in a state of remarkable transformation, where the seeds of what would become the modern internet were just beginning to sprout from the fertile ground of academic research networks and corporate innovation. Personal computers had evolved from expensive curiosities into essential business tools, yet the concept of a truly interconnected global network remained largely theoretical to most users. In this landscape of rapid technological change, few could have predicted that a programming language created in just 10 days would eventually become the foundation of nearly every interactive experience on the web. To understand the birth of JavaScript, one must first appreciate the computing environment that preceded it. The early 1990s saw the dominance of desktop applications built with languages like C and C++, where programs ran independently on individual machines with little regard for network connectivity. The World Wide Web, invented by Tim Berners-Lee at CERN in 1991, introduced a revolutionary concept: documents that could link to other documents across the globe through a simple markup language called HTML. Yet these early web pages were entirely static, offering no more interactivity than a printed magazine page. The browser landscape of this era was dominated by simple document viewers that could render text and basic images. Mosaic, developed at the National Center for Supercomputing Applications by Marc Andreessen and Eric Bina, emerged as the first truly popular graphical web browser in 1993. Its success demonstrated the immense potential of the web as a platform for information sharing, but also highlighted its limitations. Web pages could display information beautifully, but they could not respond to user actions, validate form inputs, or create the dynamic experiences that users were beginning to expect from their computing environments. Marc Andreessen, recognizing the commercial potential of the web browser, left academia to co-found Netscape Communications Corporation with Silicon Graphics founder Jim Clark in 1994. Their vision extended far beyond simple document viewing. They imagined a future where the browser would become a platform for applications that could rival traditional desktop software. However, this ambitious vision faced a significant technical hurdle. HTML, while excellent for structuring documents, lacked any mechanism for creating interactive behavior. The competitive landscape of the mid-1990s was fierce and unforgiving. Microsoft, having initially dismissed the internet as a passing trend, suddenly awakened to its potential and began developing Internet Explorer with the explicit goal of crushing Netscape. This was not merely a business rivalry, but an existential struggle for control over what many recognized would become the primary computing platform of the future. Netscape needed something revolutionary to maintain its advantage in this rapidly evolving market. In this context of intense competition and technological limitation, Netscape began exploring solutions for adding interactivity to web pages. Various approaches were considered, including embedding existing programming languages into browsers or creating entirely new development frameworks. The company needed something that would appeal to both professional programmers and the growing community of web designers who had little formal programming training. The solution would need to be simple enough for beginners, yet powerful enough to create meaningful interactive experiences. Java, developed by Sun Microsystems under the leadership of James Gosling, emerged as a significant influence on Netscape's thinking. Originally designed for embedded systems and interactive television, Java had been repositioned as a language for internet programming. Its write once, run anywhere philosophy and object-oriented design made it an attractive option for creating sophisticated web applications. Netscape formed a strategic partnership with Sun Microsystems, agreeing to support Java applets within the Netscape Navigator browser. However, Java's complexity and verbose syntax made it unsuitable for the simple scripting tasks that web designers needed to perform. Creating a Java applet required understanding complex concepts like object-oriented programming, compilation, and the Java virtual machine. Most web designers simply wanted to add basic interactivity like form validation or simple animations without needing to become full-fledged programmers. Netscape recognized the need for what they internally called a glue language, that could bridge the gap between HTML's simplicity and Java's power. The technical requirements for this new language were both specific and challenging. It needed to integrate seamlessly with HTML documents, allowing scripts to be embedded directly in web pages. The language had to be interpreted rather than compiled, enabling rapid development and deployment without complex build processes. Most importantly, it needed to provide access to the browser's document object model, allowing scripts to manipulate web page content dynamically. These requirements eliminated most existing programming languages from consideration. Netscape's management also imposed marketing constraints that would significantly influence the language's design. To maintain their partnership with Sun Microsystems and capitalize on Java's growing popularity, the new language would need to have some syntactic similarity to Java. This decision was purely strategic. There was no technical requirement for the languages to be related. In fact, the fundamental design philosophies of the two languages would prove to be quite different. Enter Brendan Eich, a 34-year-old programmer with a unique combination of skills that made him perfect for this challenging assignment. Born on July 4, 1961, in Pittsburgh, Pennsylvania, Eich had developed a passion for programming languages during his academic career. He earned his bachelor's degree in mathematics and computer science from Santa Clara University in 1985, followed by a master's degree from the University of Illinois at Urbana-Champaign in 1986. Eich's professional experience before joining Netscape had given him deep expertise in compiler design and programming language theory. At Silicon Graphics, he had worked on network monitoring tools and had gained valuable experience in creating domain-specific languages. His background included significant exposure to functional programming concepts, particularly Scheme, a dialect of Lisp known for its elegant simplicity and powerful metaprogramming capabilities. This functional programming background would prove crucial in shaping JavaScript's unique characteristics. When Eich joined Netscape in April 1995, he was initially hired with the promise of implementing Scheme in the browser. Scheme represented everything that Eich loved about programming languages: mathematical purity, syntactic simplicity, and powerful abstraction capabilities. The idea of bringing this beautiful research language to millions of web users was deeply appealing to someone with Eich's academic background. However, corporate realities would soon intervene to change this plan dramatically. The timing of Eich's arrival at Netscape coincided with intense internal discussions about the company's technology strategy. The partnership with Sun Microsystems was becoming increasingly important, and Java was beginning to dominate conversations about the future of web programming. Some within Netscape questioned whether a separate scripting language was even necessary, given that Java could theoretically handle all programming tasks within the browser. This debate would ultimately reshape Eich's assignment in ways that he could never have anticipated. The stage was now set for one of the most remarkable feats in programming history: the creation of a new programming language in just 10 days that would eventually become one of the most widely used languages in the world, fundamentally changing how people interact with digital information and laying the foundation for the modern web as we know it today. The pressure that descended upon Brendan Eich in May 1995 was unlike anything he had experienced in his programming career. What had begun as an exciting opportunity to implement Scheme in the browser had transformed into a seemingly impossible mission: create an entirely new programming language in just 10 days that would satisfy both technical requirements and corporate marketing demands. The deadline was non-negotiable, as Netscape Navigator 2.0 was scheduled for release in September, and the new scripting language needed to be included in the beta version that would ship in just a few months. The constraints imposed on Eich were both technical and political. The language had to look syntactically similar to Java to satisfy Netscape's partnership with Sun Microsystems, yet it could not be so complex as to intimidate web designers who had no formal programming training. It needed to be interpreted rather than compiled, allowing for rapid development cycles, but still powerful enough to create meaningful interactive experiences. Most challenging of all, it had to integrate seamlessly with the browser's document model, providing access to HTML elements and enabling dynamic manipulation of web page content. Ike approached this challenge by drawing inspiration from multiple programming paradigms, creating what would become one of the most unique and influential language designs in computing history. From Scheme, he borrowed the concept of functions as first-class objects and the power of lexical scoping. From Self, a prototype-based object-oriented language developed at Sun Labs, he adopted the idea of prototype-based inheritance, which eliminated the need for formal class definitions. From Java and C, he borrowed familiar syntax patterns that would make the language approachable to programmers already familiar with those languages. The name given to this new language during development was Mocha, a choice that reflected both the caffeinated urgency of its creation and perhaps Ike's appreciation for the rich, complex flavors that could emerge from simple ingredients. Working from his office at Netscape's Mountain View headquarters, Ike began what he would later describe as one of the most intense programming experiences of his life. The 10-day timeline meant that every design decision had to be made quickly and implemented immediately, with little time for extensive planning or architectural refinement. The first major challenge Ike faced was designing the language's type system. Unlike Java, which required explicit type declarations for all variables, Mocha would use dynamic typing, allowing variables to hold values of any type and determining types at runtime. This decision made the language much more approachable for beginners while providing the flexibility needed for rapid prototyping. However, it also meant that the language would need sophisticated runtime type checking and conversion mechanisms to handle the inevitable situations where different types would interact. Ike's implementation strategy was both pragmatic and ingenious. Rather than building a completely new language infrastructure from scratch, he embedded the interpreter directly into the Netscape Navigator codebase, allowing scripts to access browser functionality through a carefully designed interface. This tight integration meant that JavaScript code could immediately access and manipulate HTML elements, respond to user events, and control browser behavior in ways that no previous web technology had allowed. The syntax Ike designed for Mocha deliberately borrowed familiar patterns from C and Java, while introducing more dynamic features. Variable declarations used the var keyword, function definitions followed C-style syntax, and control structures like if statements and for loops looked reassuringly familiar to programmers. However, beneath this familiar surface lay a much more dynamic and flexible language that supported functional programming concepts, prototype-based object creation, and runtime code evaluation through the powerful eval function. One of the most innovative aspects of Ike's design was the handling of objects and inheritance. Instead of requiring formal class definitions like Java, Mocha used a prototype-based system where any object could serve as a template for creating new objects. This approach was both simpler for beginners to understand and more flexible for advanced users, though it would later prove to be a source of confusion for programmers coming from class-based languages. The integration between Mocha and the browser's document structure required Ike to design what would become known as the Document Object Model, or DOM. This interface allowed scripts to access HTML elements as objects, manipulate their properties, and respond to user interactions like mouse clicks and keyboard input. The DOM would eventually become one of the most important aspects of web programming, enabling the creation of dynamic user interfaces that could respond to user actions without requiring server communication. As the 10-day sprint progressed, Ike faced numerous design challenges that required immediate decisions. How should the language handle errors? What built-in objects and functions should be provided? How could scripts communicate with Java applets? Each of these questions needed answers that would work not just for the immediate prototype, but for the millions of web developers who would eventually use the language. The pressure was immense, but Ike's deep understanding of programming language theory allowed him to make decisions quickly while maintaining overall design coherence. The debugging and testing process during these 10 days was necessarily informal and rapid. Ike would implement a feature, test it quickly in the browser, and immediately move on to the next challenge. This iterative approach meant that some rough edges and quirks were inevitably built into the language, characteristics that would persist even as JavaScript evolved over the decades that followed. However, it also meant that the language was designed from the ground up to work in a real browser environment, rather than as an abstract theoretical exercise. By the end of the 10-day period, Ike had accomplished something remarkable, a working implementation of a new programming language that could be embedded in web pages, manipulate HTML content, respond to user events, and communicate with Java applets. The prototype was rough around the edges and lacked many features that would be added later, but it demonstrated the core concepts that would make JavaScript revolutionary. Web pages could now respond to user actions, validate form input, create animations, and provide interactive experiences that had previously been impossible. The first demonstration of Mocha to Netscape management was both exciting and nerve-wracking. Ike showed how a simple script embedded in an HTML page could respond to a button click, change text content, and manipulate the appearance of page elements. For executives who had been struggling to articulate how browsers could compete with desktop applications, this demonstration provided a concrete answer. The web was no longer limited to static documents. It could now support truly interactive applications. However, the corporate naming machine was just getting started with Ike's creation. Mocha was deemed unsuitable for marketing purposes, and the language was renamed LiveScript for its first public release. This name better captured the dynamic, living nature of web pages, enhanced with scripting capabilities. The LiveScript name appeared in early beta versions of Netscape Navigator 2.0, and developers began experimenting with the new possibilities it offered. The initial reception from the developer community was mixed, but generally positive. Web designers who had been limited to static HTML were excited by the possibilities for creating interactive experiences. However, the language's dynamic nature and loose typing system were foreign concepts to many programmers accustomed to more rigid languages like C and Java. Early adopters began sharing techniques and discovering both the power and the quirks of this new language. As summer 1995 progressed and the September release date approached, Netscape's marketing team made another decision that would have profound implications for the language's future. Seeking to capitalize on the growing popularity of Java and strengthen the partnership with Sun Microsystems, they decided to rename LiveScript once again, this time to JavaScript. This decision was purely marketing-driven. Despite the name, JavaScript shared no significant technical heritage with Java, beyond some surface syntax similarities. The JavaScript name would prove to be both a blessing and a curse for the language's adoption. On the positive side, it implied a connection to Java's growing popularity and suggested that JavaScript might be easier to learn for developers already familiar with Java syntax. However, it also created lasting confusion about the relationship between the two languages and led to unrealistic expectations about JavaScript's capabilities and design philosophy. The final beta release of Netscape Navigator 2.0 in September 1995 marked JavaScript's public debut, though few could have predicted the profound impact this hastily created language would have on the future of computing, fundamentally transforming how humans interact with digital information and laying the groundwork for an entirely new category of software applications. The release of Netscape Navigator 2.0 with JavaScript in September 1995 marked the beginning of a new era in web development, though the initial response from the broader programming community was far from universally enthusiastic. Many established software developers viewed JavaScript with skepticism, dismissing it as a toy language suitable only for creating trivial animations and simple form validations. This perception was not entirely unfair, as the early implementations of JavaScript were indeed limited in scope and plagued with performance issues that made complex applications impractical. The first JavaScript-enabled websites that appeared in late 1995 and early 1996 were often exercises in novelty rather than utility. Web developers, suddenly empowered with the ability to create dynamic content, frequently used JavaScript for what Brendan Eich himself would later describe as annoyances: scrolling text in browser status bars, flashing images, pop-up windows. and mouse cursor trails became common features that demonstrated JavaScript's capabilities, while often degrading the user experience. These early applications, while technically impressive, reinforced the perception that JavaScript was more about visual tricks than serious programming. However, beneath the surface of these seemingly frivolous applications, a more profound transformation was taking place. Web developers were beginning to understand that JavaScript provided unprecedented access to the browser environment, allowing them to create experiences that blurred the line between web pages and desktop applications. Form validation, which had previously required server round trips for every check, could now be performed instantly in the browser. Dynamic menus, interactive galleries, and real-time content updates became possible, fundamentally changing user expectations about web interface responsiveness. The technical limitations of early JavaScript implementations were significant and would shape development practices for years to come. The language interpreter was relatively slow, making computationally intensive tasks impractical. Memory management was rudimentary, leading to frequent memory leaks in complex applications. Cross-browser compatibility was virtually non-existent, as each browser vendor implemented their own version of the JavaScript specification with subtle but important differences. These constraints forced developers to adopt conservative programming practices and extensive testing procedures. Microsoft's response to JavaScript's emergence was swift and characteristically aggressive. Recognizing the threat that Netscape's innovations posed to Microsoft's dominance in personal computing, the company began developing its own scripting language for Internet Explorer. JScript, as Microsoft's implementation was called, was designed to be compatible with JavaScript while introducing Microsoft-specific extensions and improvements. This marked the beginning of what would become known as the browser wars, a period of intense competition that would drive rapid innovation while creating significant compatibility challenges for web developers. The relationship between JavaScript and Java during this early period was complex and often misunderstood. While Netscape's marketing emphasized the connection between the two languages, the technical reality was quite different. Java applets required a separate virtual machine and provided a completely different programming model focused on compiled bytecode and object-oriented design. JavaScript, by contrast, was interpreted directly by the browser and followed a more dynamic, prototype-based approach to programming. This fundamental difference meant that despite their similar names and some syntactic similarities, the two languages served very different purposes in web development. Sun Microsystems, Java's creator, had mixed feelings about JavaScript's success. On one hand, the association with Java helped promote Sun's language and reinforced the perception that Sun was at the forefront of Internet technology. On the other hand, JavaScript's simpler syntax and more immediate feedback loop made it more appealing to many developers than Java's more formal approach. This tension would influence the evolution of both languages over the coming years. The development community's gradual acceptance of JavaScript was driven largely by practical necessity rather than theoretical appreciation. As more websites began incorporating JavaScript functionality, web developers found themselves forced to learn the language regardless of their personal preferences. This practical adoption led to the emergence of the first JavaScript programming guides, tutorials, and reference materials. Publishers like O'Reilly began producing JavaScript books, and online communities started sharing techniques and solutions to common programming challenges. Netscape's internal development of JavaScript continued at a rapid pace throughout 1996. Version 1.1 introduced important new features including better error handling, improved object model access, and enhanced integration with HTML forms. The language was evolving from Brendan Eich's 10-day prototype into a more robust programming platform, though many of the fundamental design decisions made during that initial sprint remained unchanged. The standardization question began to emerge as JavaScript's popularity grew, with Microsoft developing JScript and other browser vendors considering their own scripting implementations. The web development community faced the prospect of multiple incompatible scripting languages. Netscape recognized that JavaScript's long-term success would depend on industry-wide adoption of a common standard rather than proprietary implementations that locked developers into specific browsers. Early JavaScript applications began to demonstrate the language's potential beyond simple visual effects. E-commerce sites used JavaScript to create shopping cart functionality that provided immediate feedback to users. Online forms became more sophisticated, with real-time validation and dynamic field generation. Educational websites began incorporating interactive elements that responded to student input. These applications showed that JavaScript could be a serious tool for creating meaningful user experiences. The performance characteristics of early JavaScript implementations shaped development practices in ways that would persist long after the underlying technical limitations were resolved. Developers learned to minimize DOM manipulation, cache frequently accessed objects, and avoid computationally intensive operations in favor of simpler algorithms. These optimization techniques became part of JavaScript programming culture, passed down from experienced developers to newcomers through informal mentorship and code sharing. Browser compatibility emerged as one of the most significant challenges facing JavaScript developers. While Netscape Navigator and Internet Explorer both supported JavaScript, their implementations differed in subtle but important ways. Object properties that worked in one browser might be undefined in another. Event handling mechanisms varied between browsers. Even basic functionality like opening new windows or manipulating form elements required different code for different browsers. This situation forced developers to either limit their applications to a single browser or invest significant effort in creating cross-browser compatibility layers. The emergence of server-side scripting languages during this period provided an interesting contrast to JavaScript's client-side focus. Technologies like Perl, PHP, and ASP enabled dynamic content generation on web servers, but they could not provide the immediate responsiveness that JavaScript offered in the browser. This complementary relationship between server-side and client-side scripting began to define the architecture of dynamic web applications. Documentation and learning resources for JavaScript were initially scarce and often of poor quality. Netscape provided basic reference materials, but comprehensive tutorials and best practices guides were rare. This scarcity of quality educational materials contributed to the proliferation of poor programming practices and reinforced the perception that JavaScript was not a serious programming language. Early adopters often learned JavaScript through trial and error, reverse engineering other developers' code, or adapting examples from the limited available documentation. The cultural impact of JavaScript during this early period extended beyond the technical realm. The ability for non-programmers to add interactive elements to their websites democratized web development in ways that had not been possible with earlier technologies. Graphic designers, writers, and hobbyists could now create dynamic web experiences without needing to understand complex programming concepts or server administration. This accessibility would prove to be one of JavaScript's most important characteristics, enabling a much broader community of creators to participate in web development. As 1996 drew to a close, JavaScript had established itself as an essential component of modern web development, despite its limitations and the skepticism of many traditional programmers. The language that Brendan Eich had created in 10 days was proving to have remarkable staying power, adapting to new requirements and inspiring innovative applications that pushed the boundaries of what web pages could accomplish, setting the stage for the standardization efforts and browser wars that would define the next phase of its evolution. The year 1997 would prove to be a watershed moment for JavaScript's evolution from a proprietary Netscape technology into a legitimate industry standard. As browser compatibility issues multiplied and competing implementations threatened to fragment the web development community, Netscape made a strategic decision that would fundamentally alter the language's trajectory. In early 1996, Netscape approached ECMA International, a European standards organization, with a proposal to standardize JavaScript under an open, vendor-neutral process. ECMA International, founded in 1961 as the European Computer Manufacturers Association, had established itself as a respected authority for information and communication technology standards. The organization's decision to accept Netscape's standardization proposal was significant, as it represented the first time a major web technology would be developed through an open standards process rather than controlled by a single company. This approach would prove crucial for JavaScript's long-term success and widespread adoption. The formation of Technical Committee 39, known as TC39, marked the beginning of JavaScript's transformation from a hastily created browser feature into a carefully designed programming language standard. The committee brought together representatives from major technology companies including Netscape, Microsoft, Sun Microsystems, Borland, and several others. Each company brought their own priorities and technical perspectives to the standardization process, creating a complex dynamic that would influence JavaScript's development for decades to come. Brendan Eich's role in the standardization process was both crucial and challenging. As JavaScript's original creator, he possessed unparalleled knowledge of the language's design philosophy and implementation details. However, the committee process required him to justify and explain design decisions that had been made rapidly during the original 10-day creation period, often without extensive documentation or formal specifications. Many of JavaScript's quirks and inconsistencies, which had seemed reasonable under extreme time pressure, now needed to be either formalized as intended behavior or corrected through careful specification work. The technical challenges facing TC39 were substantial. JavaScript implementations across different browsers had already begun to diverge, with each vendor adding proprietary extensions and interpreting ambiguous behaviors differently. Microsoft's JScript, while largely compatible with Netscape's JavaScript, included several Microsoft-specific features and handled certain edge cases differently. Reconciling these differences while maintaining backward compatibility with existing websites required careful negotiation and technical compromise. The committee's work was further complicated by the need to create a specification that was both technically precise and implementer-friendly. Unlike academic programming language specifications, which could focus purely on theoretical correctness, the ECMAScript specification needed to provide clear guidance for browser vendors while remaining flexible enough to accommodate different implementation strategies. This balance between precision and practicality would become a recurring theme in JavaScript's evolution. One of the most significant decisions made during the standardization process was the choice of the name ECMAScript for the standardized language. While JavaScript remained the popular name used by developers and in marketing materials, the ECMAScript name avoided trademark issues with Sun Microsystems, which owned the JavaScript trademark through its partnership with Netscape. This naming convention established a pattern where ECMAScript referred to the formal language standard while JavaScript described specific implementations of that standard. The first ECMAScript specification, officially designated ECMA 262 and published in June 1997, represented a remarkable achievement in collaborative standards development. The document captured the essential characteristics of JavaScript while providing enough detail for independent browser vendors to create compatible implementations. The specification defined the language's syntax, semantics, and built-in objects with unprecedented precision, establishing a foundation for future language evolution. However, the ECMAScript 1 standard also formalized many of JavaScript's original quirks and design inconsistencies. Features like automatic semicolon insertion, type coercion rules, and the behavior of the "this" keyword in different contexts were specified exactly as they existed in early Netscape implementations. While this approach ensured backward compatibility with existing websites, it also meant that some of JavaScript's most confusing aspects became permanent parts of the language specification. Microsoft's participation in the standardization process was both crucial and complex. As the developer of Internet Explorer and JScript, Microsoft had significant influence over the web platform's future direction. The company's involvement in TC39 demonstrated their recognition that web standards were becoming too important to ignore, but it also reflected their strategic interest in ensuring that any standard would be compatible with their existing technologies and future plans. The relationship between the ECMAScript standard and existing JavaScript implementations created interesting challenges for browser vendors. While the standard provided a clear target for implementation, many websites had already been built using browser-specific features that were not part of the ECMAScript specification. Browser vendors found themselves needing to support both the standard ECMAScript features and their own proprietary extensions to maintain compatibility with existing content. The publication of ECMAScript 1 had immediate practical benefits for web developers. For the first time, developers could refer to an authoritative specification when writing JavaScript code, rather than relying on informal documentation or reverse engineering browser behavior. This clarity was particularly valuable for resolving disputes about correct language behavior and for planning cross-browser compatibility strategies. Educational institutions and training organizations began to incorporate ECMAScript 1 into their curricula and materials. The existence of a formal standard made JavaScript appear more legitimate as a subject for serious computer science education, helping to counter the perception that it was merely a toy language for creating web page animations. Universities started offering courses that included JavaScript programming, and professional training programs began treating JavaScript as a serious development skill. The standardization process also influenced the broader web development community's approach to JavaScript programming. With a clear specification available, developers began to adopt more disciplined programming practices, writing code that conformed to the standard, rather than relying on browser-specific behaviors. This shift towards standards compliance would prove crucial as the web platform became more complex and diverse. Internet Explorer 4, released in September 1997, became the first browser to claim full support for ECMAScript 1. This milestone demonstrated that the standardization process could produce practical results, enabling Microsoft to market Internet Explorer as standards compliant while providing developers with confidence that ECMAScript features would work consistently across different browser implementations. The success of ECMAScript 1 standardization established TC39 as the authoritative body for JavaScript evolution, but it also revealed the challenges inherent in committee-based language design. The need to achieve consensus among competing companies with different technical priorities and business interests meant that future language evolution would be slower and more deliberate than the rapid innovation that had characterized JavaScript's early development. Browser performance remained a significant concern during this period, as JavaScript interpreters were still relatively slow compared to compiled languages. The ECMAScript 1 standard did not address performance issues directly, focusing instead on functional correctness and compatibility. This approach meant that while JavaScript behavior became more predictable across browsers, the language's reputation for poor performance persisted. The global nature of web development created additional challenges for the standardization process. Unlike previous programming languages that were primarily used within specific technical communities, JavaScript needed to work across different cultural, linguistic, and technical contexts. The ECMAScript specification needed to account for internationalization concerns while remaining accessible to developers worldwide. As 1997 concluded, the successful publication of ECMAScript 1 had transformed JavaScript from a proprietary browser feature into an official international standard. This achievement provided a solid foundation for the language's continued evolution while establishing precedents for collaborative web standards development that would influence many future technologies. The stage was now set for the next phase of JavaScript's evolution, as browser vendors began implementing ECMAScript 1, while the Standards Committee turned its attention to planning more ambitious improvements for future versions of the specification. The period from 1998 through the early 2000s represented both the height of JavaScript's early success and the beginning of its most challenging era. As the browser wars intensified between Netscape and Microsoft, JavaScript found itself caught in the crossfire of corporate strategies that prioritized market dominance over technical excellence. The standardization achieved with ECMAScript 1 had provided a foundation, but the practical reality of web development remained complicated by competing implementations and proprietary extensions. ECMAScript 2, published in August 1998, represented a minor but important milestone in the language's evolution. Unlike the groundbreaking first edition, ECMAScript 2 was primarily a maintenance release designed to align the ECMA 262 specification with the ISO/IEC 16262 international standard. This alignment process involved careful editorial work to ensure that the two specifications were technically identical while meeting the different formatting and procedural requirements of each standards organization. While ECMAScript 2 introduced no new language features, its publication demonstrated the maturity and stability of the standardization process established by TC39. The committee's ability to coordinate with multiple international standards bodies and maintain consistency across different specification documents provided confidence that JavaScript would continue to evolve through orderly, collaborative processes rather than fragmented vendor-specific development. The real excitement in JavaScript development during 1998 centered around practical applications rather than language specification work. Web developers were beginning to discover the true potential of dynamic HTML, combining JavaScript with cascading style sheets to create interactive user interfaces that approach the sophistication of desktop applications. Dynamic menus, collapsible content sections, and interactive forms became common features on commercial websites. However, the browser compatibility situation that had begun in 1996 was reaching crisis proportions by 1998. Internet Explorer and Netscape Navigator had evolved into fundamentally different platforms, each supporting different JavaScript APIs and interpreting the ECMAScript specification differently. The document object model implementations were particularly problematic, with each browser exposing HTML elements through incompatible object interfaces that required entirely different JavaScript code. Microsoft's aggressive pursuit of browser market share during this period had profound implications for JavaScript development. Internet Explorer 4 and 5 introduced powerful new features like XML HTTP request and advanced DHTML capabilities, but these innovations were implemented as Microsoft-specific extensions rather than open standards. Web developers faced an impossible choice: create cutting-edge applications that worked only in Internet Explorer, or limit themselves to the minimal common subset of features supported by all browsers. The dot-com boom that reached its peak around 2000 created enormous demand for interactive web applications, pushing JavaScript beyond its original design parameters. E-commerce sites needed sophisticated shopping cart functionality, online banking required secure form handling, and early web applications attempted to replicate desktop software functionality within browser constraints. These ambitious projects exposed JavaScript's limitations while demonstrating its essential role in the emerging web economy. Netscape's gradual decline during this period had significant implications for JavaScript's development. As Internet Explorer gained market share, reaching over 80% by 2001, Microsoft's proprietary extensions began to define the de facto standard for web development. Many developers abandoned attempts at cross-browser compatibility and focused exclusively on Internet Explorer, creating a generation of websites that were effectively locked to Microsoft's platform. The complexity of JavaScript development during this era cannot be overstated. A typical web application required separate code paths for different browsers, extensive feature detection routines, and careful testing across multiple platform combinations. JavaScript libraries began to emerge as developers shared solutions to common compatibility problems, but these early libraries were often browser-specific and provided incomplete abstractions over the underlying platform differences. ECMAScript 3, published in December 1999, represented the most significant enhancement to JavaScript since its original creation. This specification introduced regular expressions, try-catch exception handling, better string handling methods, and more precise definitions of numerical operations. Perhaps most importantly, ECMAScript 3 included the Use Strict directive, which enabled developers to opt into more rigorous error checking and eliminated some of JavaScript's most problematic behaviors. The regular expression support, added to ECMAScript 3, was particularly significant for web development. Pattern matching and text manipulation capabilities enabled sophisticated form validation, content processing, and data parsing that had previously required server-side processing. This enhancement moved JavaScript closer to being a general-purpose programming language rather than just a browser scripting tool. Exception handling through try-catch blocks addressed one of JavaScript's most serious shortcomings in enterprise development. Early JavaScript code had no reliable way to handle errors gracefully, leading to applications that would simply stop working when unexpected conditions occurred. The addition of structured exception handling enabled developers to create more robust applications that could recover from errors and provide meaningful feedback to users. The enhanced string manipulation methods introduced in ECMAScript 3 reflected the language's evolution toward more sophisticated text processing applications. Methods like split, replace, and match provided powerful tools for parsing and manipulating textual data, enabling JavaScript to handle complex data formats and user input processing that had previously been impractical. However, the implementation of ECMAScript 3 across different browsers was uneven and problematic. While all major browsers eventually claimed ECMAScript 3 support, the quality and completeness of their implementations varied significantly. Internet Explorer's JScript implementation had subtle but important differences from the implementations in Netscape Navigator and the emerging Mozilla browser, perpetuating the compatibility problems that plagued web development. The performance characteristics of JavaScript during this period remained a significant constraint on application development. Even with the enhancements in ECMAScript 3, JavaScript interpreters were still much slower than compiled languages, making computationally intensive applications impractical. Memory management was primitive, and garbage collection often caused noticeable pauses in user interfaces. These limitations reinforced the perception that JavaScript was suitable only for simple scripting tasks. The emergence of Mozilla as an open-source project in 1998 provided new hope for JavaScript's future development. Unlike the corporate-controlled development at Netscape and Microsoft, Mozilla represented a community-driven approach to browser development that prioritized standards compliance and technical excellence over market share considerations. Brendan Eich's continued involvement in Mozilla ensured that JavaScript's original design philosophy would influence the project's direction. Mozilla's development of the Gecko rendering engine included a completely rewritten JavaScript implementation called SpiderMonkey. This new engine was designed from the ground up to be standards compliant, efficient, and extensible. SpiderMonkey's architecture provided a foundation for future JavaScript innovations while demonstrating that open-source development could produce browser technology that competed with corporate alternatives. The relationship between JavaScript and Java during this period became increasingly strained as the two languages diverged in their development trajectories. While Java evolved toward enterprise application development with features like Enterprise Java Beans and J2EE, JavaScript remained focused on client-side web scripting. The original vision of JavaScript as a companion language to Java was largely abandoned, as developers recognized that the two languages served fundamentally different purposes. Server-side JavaScript experiments during this period, including Netscape's Livewire and various other implementations, failed to gain significant traction. The complexity of JavaScript deployment on servers, combined with the availability of more mature server-side technologies like Perl, PHP, and ASP, meant that JavaScript remained primarily a client-side technology. This limitation would persist until the eventual emergence of Node.js, nearly a decade later. The educational and cultural perception of JavaScript during the early 2000s remained problematic despite its growing technical capabilities. Many computer science programs continued to treat JavaScript as a secondary scripting language rather than a serious programming platform. The association with web page animations and simple form validation overshadowed the language's more sophisticated applications, perpetuating the perception that JavaScript was not suitable for serious software development. As the dot-com bubble burst in 2001, many ambitious JavaScript projects were abandoned or scaled back significantly. The economic downturn reduced investment in web technology innovation and forced developers to focus on more conservative, proven approaches to web development. This period of retrenchment would paradoxically create the conditions for JavaScript's eventual renaissance by forcing the development community to focus on fundamental improvements rather than flashy features. The stage was now set for what would become known as the dark ages of JavaScript development, a period when browser innovation stagnated, standards development slowed, and the web development community struggled with the legacy of incompatible implementations and abandoned technologies. Yet beneath this apparent stagnation, the foundations were being laid for the revolutionary changes that would transform JavaScript into the dominant programming platform of the 21st century. The early 2000s marked the beginning of what would later be remembered as JavaScript's dark ages, a period characterized by stagnant browser development, abandoned standards initiatives, and a general sense that web technology had reached an evolutionary dead end. The collapse of the dot-com bubble in 2001 had devastating effects on web innovation as venture capital dried up and technology companies focused on survival rather than advancement. JavaScript, caught in this broader malaise, seemed destined to remain a niche scripting language forever limited by browser compatibility issues and performance constraints. Microsoft's overwhelming dominance of the browser market by 2002 created a paradoxical situation for JavaScript development. With Internet Explorer commanding over 90% market share, Microsoft had little incentive to continue innovating or adhering to web standards. The company effectively abandoned Internet Explorer development after version 6, which was released in August 2001. This stagnation meant that JavaScript's primary deployment platform remained frozen in time, while other programming technologies continued to evolve rapidly. The impact of Microsoft's browser monopoly on JavaScript cannot be overstated. While other programming languages benefited from regular compiler improvements, new runtime features, and expanding standard libraries, JavaScript remained trapped in the feature set of Internet Explorer 6. Memory leaks, performance problems, and quirky behavior that had been acceptable during the rapid innovation of the late 1990s became permanent fixtures that developers had to work around rather than solve. Netscape's final collapse during this period removed JavaScript's original champion from the competitive landscape. AOL's acquisition of Netscape in 1999 had already reduced the company's technical influence, but the formal discontinuation of Netscape Navigator development in 2003 seemed to seal JavaScript's fate as a Microsoft-controlled technology. The vibrant competition that had driven JavaScript's early evolution was replaced by corporate indifference and technical stagnation. However, beneath the surface of this apparent decline, important developments were taking place that would eventually revolutionize JavaScript's role in web development. The Mozilla Foundation, established in 2003 as a non-profit organization dedicated to open web standards, continued Brendan Eich's work on JavaScript through the Firefox browser project. While Firefox's market share remained small during its early years, its commitment to standards compliance and innovative features provided a beacon of hope for developers frustrated with Internet Explorer's limitations. The most significant technical development during this dark period was largely invisible to most developers: Microsoft's implementation of XML HTTP request in Internet Explorer 5, released in March 2000. This seemingly minor addition to the browser's object model enabled JavaScript code to make HTTP requests to web servers without requiring a full-page reload. While the feature was originally designed to support Microsoft's Outlook web access application, its implications for web development were profound. XML HTTP request remained a Microsoft-specific feature for several years, largely ignored by the broader web development community. The complexity of cross-browser development during this period meant that most developers avoided browser-specific features, preferring to stick with the limited common subset of functionality that worked across all platforms. This conservative approach, while understandable given the circumstances, delayed recognition of XML HTTP requests' revolutionary potential. The concept that would eventually become known as AJAX existed in various forms throughout the early 2000s, but it lacked a unifying name and conceptual framework. Developers at companies like Google, Amazon, and Microsoft were experimenting with dynamic content loading and background server communication, but these techniques were considered advanced specializations rather than fundamental web development practices. The scattered nature of these experiments meant that knowledge and best practices developed slowly and inconsistently. Jesse James Garrett's essay, Ajax, A New Approach to Web Applications, published in February 2005, provided the catalyst that transformed these scattered experiments into a coherent development methodology. Garrett, working at the design consultancy Adaptive Path, coined the term Ajax as an acronym for asynchronous JavaScript and XML. More importantly, he articulated a vision of web applications that could provide desktop-like user experiences through intelligent use of background server communication. The timing of Garrett's essay was crucial to its impact. By 2005, broadband internet access was becoming common, making the performance benefits of Ajax techniques more apparent to users. Web developers were increasingly frustrated with the limitations of traditional page-based applications, and businesses were beginning to recognize the competitive advantages of superior user experiences. The confluence of these factors created an environment ready for Ajax's revolutionary message. Google's prominent adoption of Ajax techniques provided the credibility and visibility that transformed Garrett's theoretical framework into practical reality. Gmail, launched in April 2004, demonstrated that web applications could rival desktop email clients in functionality and responsiveness. Google Maps, released in February 2005, showed how Ajax could create entirely new categories of web applications that had been impossible with traditional page-based approaches. The technical implementation of Ajax applications required sophisticated JavaScript programming that pushed the language beyond its traditional role as a simple scripting tool. Developers needed to manage asynchronous callbacks, handle network errors gracefully, and coordinate complex interactions between client-side logic and server-side APIs. This complexity demanded a level of JavaScript expertise that few web developers possessed, creating a significant barrier to Ajax adoption. The XML HTTP request object, which had been languishing as a Microsoft-specific feature for 5 years, suddenly became the most important API in web development. Other browser vendors scrambled to implement compatible functionality, though the lack of a formal standard meant that each implementation had subtle differences in behavior and capability. The familiar pattern of cross-browser compatibility challenges emerged once again, but the potential benefits of Ajax development motivated developers to overcome these obstacles. Mozilla's implementation of XML HTTP request in Firefox provided the first real alternative to Internet Explorer's version, though differences in error handling, security policies, and supported features required careful programming to achieve cross-browser compatibility. The Safari and Opera browsers followed with their own implementations, each introducing additional variations that complicated Ajax development further. The security implications of Ajax applications introduced new categories of vulnerabilities that web developers were unprepared to handle. The same origin policy, which restricted XML HTTP requests to communicating only with the originating server, provided some protection, but also limited the architectural possibilities for web applications. Cross-site scripting attacks became more dangerous when combined with Ajax techniques, as malicious scripts could now communicate with external servers without user awareness. The user experience implications of Ajax development required fundamental rethinking of web application design principles. Traditional web applications provided clear feedback about their state through page loads and browser navigation indicators. Ajax applications needed to implement their own loading indicators, error messages, and state management systems. The lack of established patterns for these interactions led to inconsistent and often confusing user experiences in early Ajax applications. The development tools available for JavaScript programming during this period were primitive compared to the sophisticated environments available for other programming languages. Debugging Ajax applications required manual inspection of network traffic, primitive console logging, and extensive trial and error testing. The complexity of asynchronous programming made traditional debugging techniques inadequate, forcing developers to develop new approaches to understanding and troubleshooting their applications. Despite these challenges, the adoption of Ajax techniques accelerated rapidly throughout 2005 and 2006. Web developers who had been constrained by traditional page-based models suddenly found themselves able to create applications that approached the sophistication of desktop software. The competitive advantages of Ajax applications were so significant that businesses were willing to invest in the additional complexity and development costs required to implement them. The emergence of Ajax as a dominant web development paradigm marked the end of JavaScript's dark ages and the beginning of its transformation into a serious application development platform. The language that had been dismissed as a toy for creating simple animations was now powering sophisticated applications that challenged fundamental assumptions about the capabilities of web-based software. The success of Ajax applications demonstrated that JavaScript's limitations were often more about perception and tooling than fundamental language design, setting the stage for the remarkable renaissance that would follow. Framework development began to accelerate as developers sought to abstract away the complexity of cross-browser Ajax programming, and the stage was set for JavaScript libraries that would revolutionize web development by providing consistent APIs and sophisticated programming abstractions that would make complex web applications accessible to a much broader community of developers. The Ajax revolution that began in 2005 created an enormous demand for JavaScript expertise, but it also exposed a fundamental problem. The complexity of cross-browser development was preventing most web developers from taking advantage of these powerful new techniques. Writing JavaScript code that worked reliably across Internet Explorer, Firefox, Safari, and Opera required deep knowledge of browser quirks, inconsistent APIs, and platform-specific workarounds. This barrier to entry threatened to limit Ajax development to an elite group of expert programmers, potentially stifling the broader adoption of dynamic web applications. The solution to this crisis emerged from the open-source community in the form of JavaScript libraries that abstracted away browser differences and provided simplified APIs for common programming tasks. These libraries represented a fundamental shift in JavaScript development philosophy, moving from direct browser programming to higher-level abstractions that could hide implementation details while providing consistent behavior across platforms. The most successful of these libraries would transform JavaScript from an expert-only technology into an accessible tool for mainstream web development. Prototype, released by Sam Stevenson in February 2005, was among the first JavaScript libraries to gain widespread adoption. Developed at Basecamp for the company's internal web applications, Prototype introduced object-oriented programming patterns and functional programming concepts that were largely foreign to most JavaScript developers. The library's approach to extending built-in JavaScript objects was controversial but effective, providing familiar programming patterns for developers coming from other languages. Prototype's influence on JavaScript development extended far beyond its direct usage. The library demonstrated that JavaScript could support sophisticated programming abstractions and that browser compatibility issues could be solved through careful library design rather than requiring developers to master every browser's peculiarities. Prototype's success inspired numerous other library projects and established the pattern of community-driven JavaScript development that would dominate the next phase of the language's evolution. The emergence of Script, Calculo, Powers, created by Thomas Fuchs as a companion to Prototype, showed how JavaScript libraries could provide sophisticated visual effects and user interface components. The library's drag-and-drop functionality, animation effects, and UI controls demonstrated that web applications could achieve the polish and interactivity traditionally associated with desktop software. Script, Calculo, US, became essential for developers seeking to create visually appealing Ajax applications without implementing complex animation and interaction logic from scratch. However, it was the release of jQuery by John Resig in January 2006 that truly democratized JavaScript development and transformed the web development landscape. jQuery's revolutionary approach to DOM manipulation and event handling made complex JavaScript programming accessible to designers and developers who had previously been intimidated by the language's complexity. The library's famous motto, "Write less, do more," captured the essence of what would make jQuery the most popular JavaScript library in history. jQuery's design philosophy was fundamentally different from earlier JavaScript libraries. Instead of extending JavaScript's built-in objects or imposing complex object-oriented frameworks, jQuery provided a simple, intuitive API focused on the most common web development tasks. The library's use of CSS selectors for DOM manipulation was particularly brilliant, allowing developers to leverage their existing CSS knowledge to write JavaScript code. This approach eliminated much of the learning curve associated with JavaScript programming. The jQuery API's chainable method design enabled developers to write concise, readable code that accomplished complex tasks with minimal syntax. Operations that required dozens of lines of browser-specific code could be reduced to single jQuery statements that worked identically across all supported browsers. This dramatic reduction in code complexity and cross-browser testing burden made JavaScript development accessible to a much broader community of web professionals. The timing of jQuery's release coincided perfectly with the growing demand for Ajax applications and the increasing frustration with cross-browser compatibility issues. Web agencies and development teams that had been avoiding JavaScript due to its complexity suddenly found themselves able to create sophisticated interactive features with relatively modest investments in training and development. Time. jQuery's adoption rate was unprecedented for a JavaScript library, reaching critical mass within months of its initial release. The jQuery plugin ecosystem that emerged around the core library represented a new model for JavaScript component sharing and reuse. Instead of monolithic frameworks that required substantial architectural commitments, jQuery plugins provided focused solutions to specific problems that could be easily integrated into existing projects. This modularity made it practical for developers to incorporate advanced functionality like date pickers, image galleries, and form validation without needing to understand their internal implementation. The success of jQuery inspired numerous competing libraries, each offering different approaches to solving common JavaScript development challenges. MooTools, developed by Valerio Proietti, provided an object-oriented framework with sophisticated inheritance and modular architecture. YUI, Yahoo's user interface library, offered enterprise-grade components and comprehensive documentation. Dojo provided a complete application framework with advanced features like declarative programming and build tools. This proliferation of JavaScript libraries created both opportunities and challenges for the web development community. While developers now had access to powerful tools that simplified complex programming tasks, they also faced difficult decisions about which libraries to adopt for specific projects. The lack of interoperability between different libraries meant that choosing one often precluded using components from others, leading to fragmentation and vendor lock-in concerns. The rise of JavaScript libraries also changed the skill requirements for web developers. Instead of needing deep knowledge of browser APIs and cross-compatibility techniques, developers could focus on learning library-specific APIs and programming patterns. This shift made JavaScript development more accessible, but also created a generation of developers who understood library abstractions better than the underlying browser technologies they abstracted. Educational resources for JavaScript development began to evolve rapidly during this period as libraries made the language more approachable for mainstream developers. jQuery's excellent documentation and extensive tutorial ecosystem set new standards for technical communication in the JavaScript community. Online learning platforms began offering courses focused on library-specific development rather than raw JavaScript programming, reflecting the practical reality of modern web development. The performance implications of JavaScript libraries were initially a concern for some developers, particularly those working on high-traffic websites where every kilobyte of download size mattered. However, the productivity benefits of library-based development generally outweighed the performance costs, especially as internet connection speeds improved and browser JavaScript engines became more efficient. The time saved in development and testing often more than compensated for slightly larger download sizes. The cultural impact of JavaScript libraries extended beyond technical considerations to influence the broader perception of JavaScript as a programming language. The sophisticated applications being built with jQuery and other libraries demonstrated that JavaScript was capable of powering serious business applications, not just simple website enhancements. This perception shift attracted more experienced developers to JavaScript and elevated the language's status within the broader programming community. Browser vendors began to take notice of the patterns emerging in popular JavaScript libraries and incorporated similar functionality into native browser APIs. Features like Document Query Selector, which provided CSS selector-based DOM querying similar to jQuery's approach, were added to browser standards, partly in response to the popularity of library implementations. This feedback loop between library innovation and browser standardization would become an important driver of web platform evolution. The emergence of JavaScript libraries also influenced server-side web development, as developers sought to share code and programming patterns between client and server environments. Early experiments with server-side JavaScript using engines like Rhino and Vate were motivated partly by the desire to leverage existing JavaScript library code and developer expertise in server applications. These experiments would eventually lead to more significant developments in server-side JavaScript programming. The debugging and development tools available for JavaScript programming began to improve significantly during this period, driven partly by the increased complexity of library-based applications. Firefox's Firebug extension, developed by Joe Hewitt, provided sophisticated debugging capabilities that made it practical to develop and troubleshoot complex AJAX applications. Other browsers followed with their own developer tools, recognizing that JavaScript development had become too important to support with primitive debugging facilities. The version control and deployment practices of web development teams evolved to accommodate the increased importance of JavaScript code in their applications. JavaScript files were no longer treated as simple enhancement scripts, but as critical application components, requiring careful versioning, testing, and deployment procedures. This shift toward treating JavaScript as first-class application code would have profound implications for web development practices and team organization. As 2007 approached, JavaScript had been fundamentally transformed from a niche scripting language into the foundation of modern web application development, with libraries providing the abstraction and tooling necessary to make sophisticated programming accessible to a broad community of developers, setting the stage for even more dramatic changes that would establish JavaScript as one of the world's most important programming platforms. The year 2008 marked the beginning of a renaissance in browser technology that would fundamentally transform JavaScript's performance characteristics and expand its potential applications far beyond traditional web development. For nearly a decade, JavaScript had been constrained by slow interpreter engines that made computationally intensive applications impractical. This limitation had reinforced the perception that JavaScript was suitable only for simple scripting tasks, despite the language's growing importance in web application development. The breakthrough that would shatter these constraints came from an unexpected source: Google's entry into the browser market. Google Chrome's initial release in September 2008 introduced the Vate JavaScript engine, a revolutionary approach to JavaScript execution that prioritized performance above all other considerations. Unlike the traditional interpreters used by other browsers, Vate compiled JavaScript directly to machine code, eliminating the performance penalty associated with interpreted languages. This fundamental architectural change represented the most significant advancement in JavaScript performance since the language's creation, opening possibilities that had previously been unimaginable. The development of Vate was led by Lars Bak, a Danish computer scientist with extensive experience in virtual machine design. Bak's team at Google approached JavaScript performance as an engineering challenge rather than accepting the conventional wisdom that interpreted languages were inherently slow. Their work drew inspiration from advanced compiler techniques and garbage collection algorithms that had been developed for other programming languages but never applied to JavaScript at scale. The performance improvements delivered by Vate were dramatic and immediately apparent to developers. JavaScript code that had taken seconds to execute in other browsers could run in milliseconds in Chrome. Complex animations that had previously caused browsers to become unresponsive now ran smoothly. Mathematical computations that had been delegated to server-side code could now be performed efficiently in the browser. These improvements transformed JavaScript from a language that developers worked around into one that they could rely upon for demanding applications. The competitive response from other browser vendors was swift and intense. Mozilla accelerated development of TraceMonkey, a just-in-time compiler for Firefox's SpiderMonkey engine. Apple began work on Nitro for Safari, while Microsoft started planning significant improvements for Internet Explorer's Chakra engine. This competition, often called the JavaScript Engine Wars, drove rapid innovation in virtual machine technology and compiler optimization techniques. The broader implications of improved JavaScript performance extended far beyond faster web pages. Applications that had previously required browser plugins like Flash or Silverlight could now be implemented in pure JavaScript with acceptable performance characteristics. This shift towards standards-based development reduced the web's dependence on proprietary technologies and simplified deployment across different platforms and devices. The emergence of HTML5 as a comprehensive web application platform during this same period provided JavaScript with access to powerful new APIs that had previously been available only to native applications. The Canvas element enabled sophisticated graphics programming, while the Web Audio API provided advanced sound synthesis capabilities. Local storage APIs allowed web applications to function offline, and geolocation services enabled location-aware applications. These enhancements transformed the browser from a document viewer into a comprehensive application platform. The combination of improved JavaScript performance and expanded browser capabilities enabled the development of applications that challenged traditional assumptions about the limits of web technology. Online office suites like Google Docs demonstrated that complex productivity applications could run entirely in the browser. Web-based games began approaching the sophistication of desktop equivalents. Real-time collaboration tools enabled multiple users to work together seamlessly across different geographic locations. Ryan Dahl's work on Node.js, which began in 2009, represented perhaps the most significant expansion of JavaScript's scope since its original creation. By combining Google's Vate engine with an event-driven I/O library, Node.js enabled JavaScript to run efficiently on servers, breaking the language's traditional confinement to browser environments. This development opened entirely new categories of applications and fundamentally changed the relationship between client-side and server-side development. The architectural philosophy behind Node.js was revolutionary in the server development community. Instead of using traditional threading models that created separate execution contexts for each user request, Node.js employed a single threaded event loop that could handle thousands of concurrent connections efficiently. This approach was particularly well suited to I/O-intensive applications like web servers and real-time communication systems. The NPM package manager, created by Isaac Schluter as part of the Node.js ecosystem, established a new model for JavaScript library distribution and dependency management. Unlike the ad hoc approach to library sharing that had characterized browser JavaScript development, NPM provided a centralized registry with automated dependency resolution and version management. This infrastructure would prove crucial for the explosive growth of the JavaScript ecosystem that followed. The cultural impact of Node.js within the programming community was profound. For the first time, JavaScript developers could use their existing skills to build complete applications, from user interfaces to database access layers. This capability attracted experienced developers from other languages, while enabling front-end specialists to expand their expertise into server-side development. The result was a dramatic increase in JavaScript's visibility and credibility within the broader software development community. The timing of these performance and capability improvements coincided with the emergence of mobile computing as a dominant platform. The iPhone's introduction in 2007 had demonstrated the potential of mobile web applications, but the performance limitations of mobile JavaScript engines made complex applications impractical. The optimization techniques pioneered in desktop JavaScript engines gradually made their way to mobile platforms, enabling sophisticated mobile web applications. The standardization process for JavaScript also accelerated during this period, as TC39 recognized the need to modernize the language to support the sophisticated applications that were becoming possible. Work began on ECMAScript 5, which would introduce strict mode, JSON support, and enhanced object manipulation capabilities. These improvements addressed many of the language design issues that had accumulated over JavaScript's rapid early evolution. The development tools available for JavaScript programming improved dramatically as the language's importance in software development became undeniable. Integrated development environments began providing sophisticated debugging, profiling, and code analysis capabilities specifically designed for JavaScript. Version control systems evolved to handle the complex dependency graphs created by modern JavaScript applications. Automated testing frameworks emerged to address the quality assurance challenges posed by dynamic, event-driven applications. The rise of JavaScript frameworks during this period reflected the language's growing sophistication and the complexity of the applications being built with it. Frameworks, like Backbone.js, provided structured approaches to client-side application development, while Express.js simplified server-side development with Node.js. These frameworks demonstrated that JavaScript could support the architectural patterns and development practices associated with serious software engineering. The performance characteristics of modern JavaScript engines also enabled new approaches to web application architecture. Single-page applications, which loaded once and then updated dynamically without full-page refreshes, became practical for complex business applications. Real-time features, like live chat and collaborative editing, became standard expectations rather than impressive demonstrations of technical capability. The educational landscape for JavaScript development evolved rapidly as universities and training programs recognized the language's growing importance. Computer science curricula began treating JavaScript as a serious programming language worthy of detailed study rather than a simple scripting tool. Professional development programs emerged to help experienced developers transition from other languages to JavaScript-focused development. The economic impact of JavaScript's transformation was substantial, as businesses recognized the competitive advantages of sophisticated web applications and the cost benefits of using a single programming language across their entire technology stack. Venture capital investment in JavaScript-focused startups increased dramatically, while established companies began rewriting their applications to take advantage of modern JavaScript capabilities. As the first decade of the 21st century drew to a close, JavaScript had completed its transformation from a simple browser scripting language into a comprehensive programming platform capable of powering everything from mobile applications to server infrastructure. With performance characteristics that rivaled traditional compiled languages and an ecosystem that was expanding at an unprecedented rate, setting the stage for the explosion of innovation that would define the next decade of web development. The early 2010s marked the beginning of JavaScript's most explosive period of growth and innovation, as the performance improvements and expanded capabilities of the previous years enabled a new generation of sophisticated web applications that pushed the boundaries of what was possible in browser environments. The success of libraries like jQuery had demonstrated the value of abstraction layers, but the complexity of modern web applications demanded more comprehensive solutions than simple DOM manipulation libraries could provide. This need gave rise to a new category of JavaScript frameworks that would fundamentally reshape how developers approached application architecture. The emergence of single-page applications as a dominant pattern in web development created unprecedented challenges for JavaScript developers. Unlike traditional web applications that relied on server-generated pages and simple client-side enhancements, SPAs required managing complex application state, handling sophisticated user interactions, and coordinating data synchronization between client and server. These requirements demanded architectural patterns and development practices that had not been necessary in earlier JavaScript applications. Backbone JS, created by Jeremy Ashkenaz and released in 2010, was among the first frameworks to provide a structured approach to client-side application development. Drawing inspiration from the model view controller pattern, common in server-side frameworks, Backbone provided a foundation for organizing JavaScript code into maintainable, testable components. The framework's minimalist philosophy and clear separation of concerns made it popular among developers who wanted structure without excessive complexity. The influence of Backbone JS extended far beyond its direct usage, as it established patterns and conventions that would influence JavaScript framework development for years to come. The concept of models, views, and routers as fundamental building blocks of client-side applications became widely accepted. The event-driven communication patterns that Backbone popularized provided a foundation for building loosely coupled, maintainable applications. Most importantly, Backbone demonstrated that JavaScript applications could benefit from the same architectural principles that governed server-side development. However, Backbone's minimalist approach also exposed the complexity inherent in client-side application development. Developers found themselves writing substantial amounts of boilerplate code to handle common patterns like data binding, view updates, and state management. The manual nature of these operations made applications error-prone and difficult to maintain as they grew in complexity. This friction created demand for more comprehensive solutions that could automate routine tasks while maintaining architectural clarity. AngularJS, developed by Mishko Hevry at Google and released in 2010, represented a radically different approach to JavaScript framework design. Instead of providing minimal structure like Backbone, Angular offered a comprehensive platform that included data binding, dependency injection, templating, and testing infrastructure. The framework's declarative approach to UI development allowed developers to describe what they wanted rather than how to achieve it, dramatically reducing the amount of imperative code required for complex applications. The two-way data binding that Angular introduced was revolutionary for JavaScript development. Instead of manually updating the DOM when application data changed, developers could declare relationships between data and view elements that would be maintained automatically by the framework. This approach eliminated entire categories of bugs related to view synchronization while making applications more responsive and interactive. Angular's dependency injection system brought enterprise software development patterns to JavaScript applications. Instead of creating complex dependency chains through global variables or manual object instantiation, developers could declare their dependencies and let the framework handle object creation and lifecycle management. This approach made applications more modular and testable while reducing coupling between components. The directive system that Angular introduced provided a powerful mechanism for creating reusable UI components. Developers could encapsulate complex functionality into custom HTML elements that could be used throughout their applications. This component-based approach to development would prove to be one of Angular's most influential contributions to JavaScript framework design, establishing patterns that would be adopted by virtually every subsequent framework. The testing infrastructure that Angular provided addressed one of JavaScript development's most persistent challenges. The framework was designed from the ground up to support unit testing, integration testing, and end-to-end testing. This emphasis on testability reflected the growing recognition that JavaScript applications required the same quality assurance practices as other software projects. Despite Angular's initial success, The framework's complexity and learning curve made it challenging for many developers to adopt. The extensive use of new concepts like dependency injection and custom directives required significant investment in learning framework-specific patterns. The debugging experience could be opaque, as the framework's magic often made it difficult to understand what was happening when things went wrong. Facebook's development of React, which began in 2011 and was open-sourced in 2013, represented yet another revolutionary approach to JavaScript application development. Instead of providing a comprehensive framework like Angular, React focused specifically on the problem of building user interfaces through a component-based architecture that emphasized predictability and developer experience. The virtual DOM concept that React introduced solved one of the most challenging aspects of dynamic web application development, efficiently updating the user interface in response to data changes. Instead of manually manipulating DOM elements or relying on complex data binding systems, React applications described their desired UI state as a function of application data. The framework then handled the efficient translation of these descriptions into actual DOM updates. React's component model provided a clean abstraction for building complex user interfaces from simple, reusable pieces. Each component encapsulated its own state and rendering logic, making it easy to reason about and test in isolation. The hierarchical composition of components provided a natural way to organize application complexity while maintaining clear boundaries between different parts of the system. The unidirectional data flow that React enforced made application behavior more predictable and easier to debug. Instead of the complex bidirectional bindings that characterized other frameworks, React applications passed data down through component hierarchies and handled user interactions through callback functions. This approach eliminated many of the timing and synchronization issues that plagued more complex data binding systems. JSX, React's syntax extension that allowed mixing JavaScript and HTML-like syntax, was initially controversial, but proved to be one of the framework's most important innovations. By treating UI descriptions as first-class JavaScript expressions, JSX enabled powerful composition patterns and made it easy to build dynamic interfaces through familiar programming constructs like loops and conditionals. The React ecosystem that emerged around the core library demonstrated a new model for JavaScript framework development. Instead of providing every possible feature in a monolithic package, React focused on doing one thing exceptionally well and enabled a rich ecosystem of complementary libraries. Flux, and later Redux, provided state management patterns, React Router handled navigation, and numerous other libraries addressed specific application needs. Vue.js, created by Evan You and first released in February 2014, represented an attempt to combine the best aspects of Angular and React, while remaining approachable for developers of all skill levels. Vue's progressive adoption model allowed developers to introduce the framework gradually into existing projects, starting with simple enhancements and expanding to full application development as their needs evolved. The template syntax that Vue provided struck a balance between the power of JSX and the familiarity of traditional HTML templates. Developers could use standard HTML with special directives to add dynamic behavior, making the framework accessible to designers and front-end developers who were not comfortable with more programmatic approaches to UI development. Vue's component system borrowed heavily from React's innovations while adding conveniences like single-file components that combined template, logic, and styling in a single file. This approach simplified the development workflow while maintaining clear separation of concerns. The framework's excellent documentation and gentle learning curve made it popular among developers who found other frameworks too complex or opinionated. The emergence of these competing frameworks created a vibrant but sometimes overwhelming ecosystem for JavaScript developers. Each framework offered different trade-offs between complexity, performance, and developer experience. The choice of framework often depended on team expertise, project requirements, and organizational preferences, rather than clear technical superiority. The tooling ecosystem that emerged around modern JavaScript frameworks reflected the increasing sophistication of web application development. Build tools like Webpack enabled complex asset processing and module bundling. Task runners like Gulp and Grunt automated development workflows. Package managers like NPM and later Yarn simplified dependency management. These tools transformed JavaScript development from a simple scripting environment into a comprehensive software engineering platform. The performance implications of framework-based development became increasingly important as applications grew in complexity. While frameworks provided significant productivity benefits, they also introduced overhead in terms of bundle size and runtime performance. Framework authors and the broader community invested heavily in optimization techniques like tree shaking, code splitting, and server-side rendering to mitigate these costs. The mobile-first approach to web development that emerged during this period influenced framework design significantly. Responsive design patterns, touch interaction handling, and performance optimization for mobile devices became standard considerations for framework developers. The rise of progressive web applications as a bridge between web and native mobile development created new requirements for offline functionality and native-like user experiences. The TypeScript programming language, developed by Microsoft and first released in 2012, gained significant traction within the JavaScript framework community as applications became more complex. TypeScript's static type system provided compile-time error checking and improved developer tooling while maintaining full compatibility with existing JavaScript code. Major frameworks began providing TypeScript support, and some, like Angular 2 and later, adopted TypeScript as their primary development language. As the 2010s progressed, JavaScript had evolved from a simple scripting language into the foundation of a sophisticated application development ecosystem, with frameworks providing the architectural patterns and tooling necessary to build applications that rivaled native software in functionality and user experience, establishing JavaScript as the dominant language for front-end development and setting the stage for its continued expansion into new domains and platforms. The period from 2009 to 2015 represented a critical juncture in JavaScript's evolution, as the language itself had remained largely unchanged since ECMAScript 3 in 1999, while the applications built with it had become exponentially more sophisticated. The frameworks and libraries that had emerged during the early 2010s demonstrated JavaScript's potential, but they also exposed fundamental limitations in the language's syntax and capabilities that made complex application development unnecessarily difficult. The ECMAScript standardization process, which had been dormant for nearly a decade, needed to be revitalized to address these growing pains. The ECMAScript 4 specification, which had been abandoned in 2008 after years of contentious debate, had attempted to introduce radical changes that would have made JavaScript into a fundamentally different language. The failure of that effort left the JavaScript community in an unusual position. While other programming languages evolved regularly to meet new requirements, JavaScript remained frozen in a feature set designed for much simpler applications. This stagnation became increasingly problematic as developers attempted to build sophisticated applications with language constructs designed for basic scripting. TC39's decision to resume active development of the ECMAScript specification in 2009 marked the beginning of JavaScript's transformation into a modern programming language. The committee adopted a more conservative approach than the failed ECMAScript 4 effort, focusing on evolutionary improvements that maintained backward compatibility while adding carefully designed features that addressed real-world development challenges. This philosophy of gradual enhancement would prove crucial for gaining broad industry support. ECMAScript 5, finalized in December 2009, represented the first significant update to JavaScript in a decade. The specification introduced strict mode, which eliminated many of JavaScript's most problematic behaviors and provided a cleaner programming model for new applications. The JSON object provided native support for the data interchange format that had become ubiquitous in web applications. Enhanced object manipulation methods like object, create, and property descriptors enabled more sophisticated programming patterns. The strict mode introduced in ECMAScript 5 was particularly significant for large-scale application development. By adding use-strict declarations to functions or entire scripts, developers could opt into more rigorous error checking that caught common programming mistakes and prevented the use of problematic language features. Variables had to be declared before use, eliminating accidental global variable creation. The problematic with statement was prohibited, and many other sources of confusion were addressed. However, the most transformative ECMAScript specification would be ECMAScript 6, also known as ECMAScript 2015 or ES6. This specification, finalized in June 2015, represented the most significant enhancement to JavaScript since its original creation. The scope and ambition of ES6 reflected the committee's recognition that JavaScript needed fundamental improvements to support the sophisticated applications that developers were building. The class syntax introduced in ES6 provided a more familiar programming model for developers coming from object-oriented languages, while maintaining JavaScript's prototypal inheritance underneath. This syntactic sugar made JavaScript more approachable for enterprise developers, while preserving the flexibility that had made the language attractive to functional programming enthusiasts. The class syntax also provided a cleaner foundation for the component-based architectures that were becoming dominant in front-end development. Arrow functions, one of ES6's most visible additions, addressed both syntactic verbosity and the confusing behavior of the "this" keyword in callback-intensive JavaScript applications. The concise syntax made functional programming patterns more readable, while the lexical binding of "this" eliminated a major source of bugs in event-driven applications. These improvements were particularly valuable for the complex, asynchronous programming patterns that characterized modern web applications. The module system introduced in ES6 finally provided JavaScript with native support for organizing code into reusable components. Unlike the ad hoc module patterns that had evolved in the JavaScript community, ES6 modules provided static analysis capabilities that enabled better tooling and optimization. The import and export syntax was clean and intuitive, while the module loader specification provided a foundation for sophisticated build tools and dependency management systems. Template literals offered a much-needed improvement to JavaScript's string handling capabilities, enabling multi-line strings and embedded expressions with an elegant syntax. This feature was particularly valuable for developers working with HTML templates, SQL queries, or any situation requiring complex string construction. The tagged template literal feature provided a foundation for building domain-specific languages within JavaScript. Destructuring assignment provided a concise syntax for extracting values from objects and arrays, reducing the boilerplate code required for common data manipulation tasks. This feature was especially valuable in functional programming contexts, where data transformation was a central concern. The combination of destructuring with default parameters and REST syntax created powerful patterns for function, definition, and invocation. Promises, while not entirely new to the JavaScript ecosystem, received native language support in ES6 that standardized asynchronous programming patterns. The Promise API provided a cleaner alternative to callback-based programming that had become unwieldy as applications grew in complexity. The standardization of promises also enabled the development of more sophisticated, asynchronous control flow patterns like async and await in future specifications. The symbol primitive type introduced a new category of property keys that could not conflict with string-based properties, enabling library developers to add functionality to objects without risking naming collisions. This capability was particularly important for framework developers who needed to attach metadata or behavior to user objects without interfering with application code. Iterators and generators provided powerful new abstractions for working with sequences of data. The iterator protocol enabled objects to participate in, for, of loops and other language constructs, while generators provided a mechanism for creating iterators with clean, readable syntax. These features enabled functional programming patterns that had previously required complex library implementations. The map and set data structures filled important gaps in JavaScript's collection types, providing alternatives to using objects as dictionaries and arrays for unique value storage. These collections offered better performance characteristics for certain use cases, while providing cleaner APIs for common operations. The weak map and weak set variants provided garbage collection-friendly alternatives for scenarios where strong references were problematic. Block-scoped variables through let and const declarations addressed one of JavaScript's most confusing aspects: variable hoisting and function scope. The new declarations provided more predictable scoping behavior that aligned with developer expectations from other languages. The const declaration enabled immutable bindings that supported functional programming patterns while catching common assignment errors. The implementation of ES6 across different JavaScript engines proved to be a complex undertaking that took several years to complete. Unlike previous ECMAScript specifications that introduced relatively modest changes, ES6 represented a fundamental expansion of the language that required significant engineering investment from browser vendors and Node.js maintainers. The staggered implementation across different environments created new challenges for developers who wanted to use modern language features. Transpilation emerged as a crucial bridge technology that enabled developers to use ES6 features while maintaining compatibility with older JavaScript engines. Tools like Babel transformed modern JavaScript syntax into equivalent code that could run on older browsers, enabling widespread adoption of new language features years before native support was universal. This approach established a pattern where JavaScript developers could use cutting-edge language features through tooling rather than waiting for universal browser support. The success of ES6 and the positive developer response encouraged TC39 to adopt an annual release cycle for ECMAScript specifications. Instead of the massive, infrequent updates that had characterized previous development, the committee began releasing smaller, focused improvements on a predictable schedule. This approach made it easier for implementers to keep up with changes while providing developers with a steady stream of language improvements. ECMAScript 2016, the first specification released under the new annual cycle, introduced relatively modest but valuable improvements, including the exponentiation operator, array, prototype, includes, and improvements to regular expressions. The smaller scope of this release demonstrated that the annual cycle could deliver meaningful improvements without the complexity and risk associated with massive specification updates. The modern ECMAScript development process also became more transparent and community-driven, with GitHub repositories for specification development and extensive public discussion of proposed features. This openness enabled JavaScript developers to participate in language design discussions and provide feedback on proposed features before they were finalized. The result was a more responsive standardization process that better addressed real-world development needs. The cultural impact of modern ECMAScript development extended beyond the technical improvements to influence how developers thought about JavaScript as a programming language. The regular introduction of new features and the adoption of modern programming language research made JavaScript feel like a living, evolving platform rather than a legacy technology with historical baggage. This perception shift attracted developers from other languages while reinvigorating the existing JavaScript community. As the 2010s progressed, JavaScript had transformed from a language with significant historical limitations into a modern programming platform that could compete with any other language in terms of expressiveness, performance, and developer experience, with a standardization process that ensured continued evolution to meet the changing needs of software development, establishing the foundation for JavaScript's expansion into virtually every domain of computing. The modernization of JavaScript through ECMAScript 6 and the annual release cycle that followed coincided with an unprecedented expansion of the language beyond its traditional browser boundaries. The combination of improved performance through modern JavaScript engines, the comprehensive feature set, provided by ES6 and the mature ecosystem that had developed around Node.js created conditions that enabled JavaScript to invade virtually every domain of software development. What had begun as a simple browser scripting language was rapidly becoming a universal programming platform that challenged the dominance of established technologies across the entire computing landscape. The mobile application development space represented one of JavaScript's most significant territorial expansions during the mid-2010s. Native mobile development had traditionally required platform-specific languages like Objective-C for iOS and Java for Android, creating substantial barriers for web developers who wanted to build mobile applications. The emergence of hybrid development frameworks that leveraged JavaScript offered an attractive alternative that promised to reduce development costs while leveraging existing web development skills. PhoneGap, later renamed Apache Cordova, had pioneered the concept of JavaScript-based mobile development by wrapping web applications in native containers that could access device APIs. However, the performance limitations and user experience compromises of early hybrid applications had limited their adoption for sophisticated mobile applications. The performance improvements in JavaScript engines and the availability of more powerful mobile hardware began to make hybrid development more viable for a broader range of applications. React Native, introduced by Facebook in 2015, represented a revolutionary approach to JavaScript-based mobile development that addressed many of the limitations of traditional hybrid frameworks. Instead of running web applications inside native containers, React Native used JavaScript to drive native user interface components, providing performance and user experience that approached native applications while maintaining the development productivity benefits of JavaScript. The architectural innovation of React Native was profound. JavaScript code controlled native user interface elements through a bridge that handled communication between the JavaScript runtime and the native platform. This approach enabled developers to use familiar React programming patterns while producing applications that felt genuinely native to each platform. The success of React Native demonstrated that JavaScript could compete with native development technologies even in performance-critical mobile applications. Flutter, Google's response to React Native, initially used the Dart programming language but later added JavaScript support, recognizing the importance of leveraging existing developer skills and ecosystem investments. The competition between these frameworks drove rapid innovation in JavaScript-based mobile development while demonstrating the viability of cross-platform approaches for serious commercial applications. Desktop application development represented another domain where JavaScript began to challenge established technologies. Electron, originally developed by GitHub as Atom Shell in 2013, enabled developers to build desktop applications using web technologies, including HTML, CSS, and JavaScript. The framework wrapped Chromium and Node.js into a runtime that could execute web applications as native desktop software, providing access to operating system APIs through JavaScript interfaces. The applications built with Electron demonstrated JavaScript's viability for sophisticated desktop software development. Visual Studio Code, Microsoft's popular code editor, was built entirely with web technologies running on Electron. Slack, Discord, and numerous other successful desktop applications proved that JavaScript-based development could produce software that competed effectively with traditional native applications. The development productivity benefits of using existing web technologies and the ability to share code between web and desktop versions made Electron attractive for many software teams. However, Electron applications also faced criticism for their resource consumption and performance characteristics compared to native alternatives. The overhead of running a complete browser engine for each application created memory and battery life concerns, particularly on mobile devices. These trade-offs sparked ongoing debates about the appropriate use cases for JavaScript-based desktop development versus traditional native technologies. The Internet of Things emerged as an unexpected but significant domain for JavaScript expansion, as the language's event-driven programming model proved well suited to the asynchronous, network-centric nature of IoT applications. Node.js's efficient handling of concurrent connections made it attractive for building IoT backend services, while the emergence of JavaScript runtimes for embedded devices enabled client-side IoT development as well. Johnny 5, a JavaScript robotics and IoT platform created by Rick Waldron, demonstrated that JavaScript could control hardware directly through interfaces like Arduino and Raspberry Pi. The ability to program hardware using the same language and programming patterns used for web development lowered the barrier to entry for IoT development while enabling rapid prototyping and experimentation. Espruino, a JavaScript interpreter designed specifically for microcontrollers, enabled JavaScript to run on extremely resource-constrained devices. This development brought JavaScript to the edge of the computing spectrum, from billion-dollar data centers to dollar microcontrollers, demonstrating the language's remarkable versatility and the universal applicability of its programming model. The emergence of serverless computing platforms represented another area where JavaScript's characteristics aligned well with new architectural patterns. AWS Lambda, introduced in 2014 with Node.js as one of its initial supported runtimes, enabled developers to run JavaScript code in response to events without managing servers. The stateless, event-driven nature of serverless computing matched JavaScript's programming model perfectly. The rapid startup times and efficient resource utilization of modern JavaScript engines made the language particularly suitable for serverless execution models, where functions needed to initialize quickly and handle requests efficiently. The extensive NPM ecosystem provided ready-made solutions for common serverless use cases, while the familiar JavaScript syntax reduced the learning curve for developers adopting serverless architectures. Machine learning and artificial intelligence applications began to incorporate JavaScript as the language's performance improved and specialized libraries became available. TensorFlow.js, Google's JavaScript implementation of their popular machine learning framework, enabled developers to run machine learning models directly in browsers or Node.js environments. This capability opened new possibilities for privacy-preserving machine learning applications that could process data locally rather than sending it to remote servers. The ability to run machine learning inference in browsers had significant implications for user experience and privacy. Applications could provide immediate feedback on user inputs, create interactive educational experiences, and process sensitive data without network transmission. The combination of JavaScript's ubiquity and machine learning capabilities enabled new categories of intelligent web applications. Blockchain and cryptocurrency applications embraced JavaScript as the ecosystem developed, with libraries like Web3.js enabling browser-based interaction with blockchain networks. The decentralized nature of blockchain applications aligned well with JavaScript's client-side execution model, while the language's JSON handling capabilities simplified working with blockchain data formats. Smart contract development platforms began supporting JavaScript, enabling web developers to participate in blockchain application development without learning specialized languages. The familiarity of JavaScript syntax and the availability of existing development tools made blockchain development more accessible to the broader software development community. Virtual and augmented reality applications found JavaScript support through WebXR APIs and frameworks like a frame that enabled VR development using familiar web technologies. The ability to create immersive experiences using JavaScript lowered the barrier to entry for VR development, while enabling the creation of VR applications that could run in standard web browsers without requiring specialized software. Installation. Game development experienced a renaissance with JavaScript as engine performance improved and game-focused libraries matured. Frameworks like Phaser provided comprehensive game development platforms built entirely in JavaScript, while the HTML5 canvas and WebGL APIs enabled sophisticated graphics programming. The ability to distribute games through web browsers without requiring App Store approval made JavaScript an attractive platform for indie game developers. The database layer of software applications also began to embrace JavaScript through technologies like MongoDB's JavaScript query language and CouchDB's JavaScript-based MapReduce functions. NoSQL databases that stored documents in JSON format aligned naturally with JavaScript's object model, creating seamless integration between application logic and data storage. Build tools and development workflows evolved to support JavaScript's expansion across multiple domains. Webpack, Rollup, and other bundlers enabled sophisticated code organization and optimization for different deployment targets. Package managers like NPM and Yarn simplified dependency management across diverse JavaScript applications. Development environments provided integrated support for multiple JavaScript runtime environments. The cultural impact of JavaScript's universal expansion was profound, as developers could now use a single programming language across their entire technology stack. This JavaScript everywhere phenomenon reduced context switching between different programming languages while enabling code sharing between different application layers. Teams could leverage JavaScript expertise across multiple domains rather than requiring specialists for each technology platform. Educational institutions began recognizing JavaScript's universal applicability and restructured their curricula to reflect the language's importance across multiple computing domains. JavaScript bootcamps and training programs proliferated as the demand for JavaScript skills expanded beyond web development into mobile, desktop, IoT, and other application areas. As the 2010s drew to a close, JavaScript had achieved something unprecedented in programming language history: universal applicability across virtually every domain of software development, from tiny microcontrollers to massive data centers, from simple web pages to sophisticated virtual reality experiences, establishing itself as the closest thing to a truly universal programming language that the software industry had ever seen. The current era of JavaScript development, spanning from the late 2010s through today, represents the culmination of nearly 3 decades of evolution that has transformed a hastily created browser scripting language into the dominant programming platform of the 21st century. As we survey the JavaScript landscape in 2025, the language's ubiquity and sophistication would be unrecognizable to developers from its early years, yet the core principles of accessibility, flexibility, and rapid iteration that Brendan Eich embedded in those original 10 days of development continue to drive its evolution. The ECMAScript annual release cycle that began with ES 2016 has delivered consistent, incremental improvements that have modernized JavaScript without breaking compatibility with existing applications. ECMAScript 2017 introduced async and await syntax that revolutionized asynchronous programming by making it as readable as synchronous code. Object, entries, and object. Values provided convenient methods for object manipulation, while string padding methods addressed common formatting needs. Shared array buffers enabled true parallelism in JavaScript applications for the first time. ECMAScript 2018 brought regular expression improvements, including named capture groups and look-behind assertions, along with rest and spread operators for objects that complemented the existing array operators. The promise. In Leopard, finally method provided better cleanup capabilities for asynchronous operations, while template literal revisions enabled more sophisticated domain-specific language implementations. The optional catch binding introduced in ES 2018 reflected the maturation of JavaScript error handling practices, allowing developers to catch errors without necessarily needing to examine the error object. This seemingly minor change demonstrated how the standardization process had become responsive to real-world usage patterns rather than purely theoretical considerations. ECMAScript 2019 introduced several features that addressed long-standing developer pain points. Array, flat, and array. FlatMap provided native solutions for common array manipulation tasks that had previously required library implementations. Object. From entries complemented object. Entries to enable round-trip transformations. String, trim start, and string Trimend offered more precise alternatives to the generic trim method. The optional catch binding and JSON stringify improvements in ES 2019 showed the committee's attention to both developer ergonomics and edge case handling. These incremental improvements might seem modest compared to the revolutionary changes of ES6, but their cumulative effect has been to eliminate friction points and provide native solutions for common programming patterns. ECMAScript 2020 marked a significant milestone with the introduction of optional chaining and nullish coalescing operators that addressed some of JavaScript's most frustrating characteristics. The optional chaining operator enabled safe property access through potentially null or undefined references, eliminating the verbose conditional checking that had plagued JavaScript applications. The nullish coalescing operator provided precise control over default value assignment, distinguishing between genuinely missing values and falsy values like zero or empty strings. The BigInt primitive type introduced in ES 2020 enabled JavaScript to handle arbitrary precision integers, addressing mathematical limitations that had constrained certain categories of applications. Dynamic imports provided a native mechanism for code splitting and lazy loading that had previously required build tool implementations. The promise. All settled method offered better control over batch asynchronous operations compared to the all-or-nothing behavior of promise. This standardization effort resolved inconsistencies in how different JavaScript environments exposed the global object, simplifying cross-platform development. String. Matchall provided a more convenient API for working with regular expression matches, while import, meta, gave modules access to their own metadata. ECMAScript 2021 continued the pattern of incremental improvements with logical assignment operators that combined logical operations with assignment, reducing boilerplate in common programming patterns. Numeric separators improved the readability of large numbers in source code, while promise provided a race condition operator that resolved with the first successful promise rather than the first settled promise. The replace all method for strings addressed a surprising gap in JavaScript's string manipulation capabilities, while weak refs and finalization registry provided advanced memory management capabilities for specialized use cases. These features demonstrated the committee's attention to both common developer needs and edge cases that affected sophisticated applications. ECMAScript 2022 introduced top-level await, one of the most anticipated features in recent memory, which enabled module initialization patterns that had been impossible with traditional module loading. The at method for arrays provided negative indexing capabilities similar to Python, while object hasown offered a more reliable alternative to hasown property for property checking. The class fields and private methods specification finally provided true encapsulation capabilities for JavaScript classes, addressing criticisms that had persisted since the introduction of class syntax in ES6. Error cause chaining enabled better error handling in complex applications where errors needed to propagate through multiple abstraction layers. The regex match indices feature provided access to substring positions in regular expression matches, enabling more sophisticated text processing applications. These improvements reflected the continued expansion of JavaScript into domains that required advanced string and data processing capabilities. ECMAScript 2023 and 2024 continued this trajectory with features like array methods for finding elements from the end, grouped object manipulation methods, and improved regular expression capabilities. The consistent delivery of useful features on an annual schedule has created predictable improvement cycles that enable developers to plan their adoption of new language capabilities. The modern JavaScript ecosystem that has emerged around these language improvements represents one of the most sophisticated software development environments ever created. The NPM registry now contains over 2 million packages, representing an unprecedented wealth of reusable code that addresses virtually every conceivable programming need. The quality and diversity of available libraries has made JavaScript development remarkably productive while reducing the need to implement common functionality from scratch. The tooling ecosystem surrounding JavaScript has evolved to match the complexity of modern applications. Build tools like Vite and EaseBuild provide near instantaneous compilation and hot reloading for rapid development cycles. Type checking through TypeScript has become standard practice for large applications, providing compile-time error detection while maintaining JavaScript's runtime flexibility. Testing frameworks like Jest and vtest enable comprehensive automated testing strategies that ensure application quality as complexity increases. The performance characteristics of modern JavaScript engines continue to improve through advanced optimization techniques that approach or exceed the performance of traditionally compiled languages for many use cases. Just-in-time compilation, sophisticated garbage collection, and aggressive optimization passes enable JavaScript applications to handle workloads that would have been unthinkable in earlier eras. WebAssembly's emergence as a compilation target for other languages has created interesting dynamics within the JavaScript ecosystem. Rather than replacing JavaScript, WebAssembly has become a complementary technology that enables performance-critical components to be implemented in languages like Rust or C++, while maintaining JavaScript for application logic and user interface. Development. This hybrid approach leverages the strengths of both technologies while addressing the specific needs of different application components. The cloud-native development practices that have become standard in modern software development align well with JavaScript's characteristics. Containerization technologies like Docker work seamlessly with Node.js applications, while orchestration platforms like Kubernetes provide sophisticated deployment and scaling capabilities for JavaScript-based services. The stateless, event-driven nature of many JavaScript applications maps well to cloud architectures that emphasize horizontal scaling and fault tolerance. The artificial intelligence and machine learning revolution has found JavaScript to be a capable platform through libraries like TensorFlow.js, Brain.js, and ML5.js. The ability to run machine learning models directly in browsers or Node.js environments has enabled new categories of intelligent applications while preserving user privacy through local data processing. The integration of AI capabilities into web applications has become increasingly seamless as these libraries have matured. Edge computing platforms have embraced JavaScript as a primary development language, with services like Cloudflare Workers, Vercel Edge Functions, and AWS Lambda at Edge, enabling JavaScript code to run closer to users for improved performance and reduced latency. The lightweight nature of JavaScript execution makes it well suited to edge environments where resource constraints and cold start times are critical considerations. The developer experience improvements that characterize modern JavaScript development would astonish developers from earlier eras. Integrated development environments provide sophisticated debugging, profiling, and refactoring capabilities specifically designed for JavaScript. Package managers handle complex dependency graphs automatically while ensuring security and compatibility. Development servers provide instant feedback on code changes while maintaining application state. The educational resources available for JavaScript learning have evolved from scarce and often inaccurate documentation to comprehensive, interactive platforms that make the language accessible to developers of all backgrounds. Online courses, interactive tutorials, and extensive documentation have democratized access to JavaScript expertise, while community resources like Stack Overflow and GitHub provide collaborative problem-solving capabilities. The global impact of JavaScript's evolution extends far beyond the software industry to influence how people interact with technology in their daily lives. The sophisticated web applications enabled by modern JavaScript have transformed commerce, education, entertainment, and communication. The accessibility of JavaScript development has enabled individuals and organizations worldwide to create digital solutions without requiring extensive technical infrastructure. As we look toward the future, JavaScript's continued evolution seems assured through the mature standardization process that balances innovation with stability. Proposals for future ECMAScript versions address emerging needs like better support for immutable data structures enhanced concurrency capabilities, and improved integration with system-level APIs. The language continues to adapt to new computing paradigms while maintaining the accessibility and flexibility that have driven its remarkable success. The story of JavaScript represents one of the most extraordinary achievements in the history of computing, a programming language created under extreme time pressure that not only survived but thrived to become the foundation of the modern digital world. From Brendan Eich's 10-day sprint in May 1995 to today's sophisticated ecosystem supporting millions of developers worldwide, JavaScript has demonstrated that accessibility, pragmatism, and community-driven evolution can create technologies that transform civilization itself, ensuring that the web remains an open, innovative platform where anyone with an idea and the determination to learn can build applications that reach billions of users across the globe.